Also begin by first thanking the organizers for having me here and setting up this beautiful workshop. Yeah, so you see the title of my talk. I will talk about thermodynamics and hydrodynamics in classical Solitons theories. There was a small change in the title. Initially, I planned to talk also about quantum soliton theories. Then I decided to drop it. But I hope it's not a big deal. We already had a few nice talks about quantum soliton systems already in the beginning of this week by Xenophon, by Fabian, Jacopo, and also, after all, Joachim talk about quantum solitons. So I'll be purely talking purely about classical soliton systems. So the work I'll be presenting I've done in collaboration with Alexander Gamayun, also from the University of Amsterdam. But let me, before I delve into technicalities, let me briefly explain what are the main objectives or the main motivation for studying classical systems, since this workshop is basically about transporting quantum system, right? So here I give like three main motivations. So the first one is, pretty general, and is this one of the kind of grand goals of statistical physics, which is to explain and derive the microscopic, explain and derive the phenomenological laws of physics, like transport directly from the microscopic interactions, which is a pretty challenging task, and probably it's only possible for exactly solvable models. So this explains why we would like to understand how these things happen in exactly solvable models. In particular, it's a good question whether one can see integrable models as representative models of various non-equilibrium transport phenomena which occur in many body systems, ranging from ballistic transport, which we've seen already, and or normal diffusion or anomalous diffusion and things like that. Second motivation is, so we had this talk on Tuesday by Jacopo when he was explaining how to use a recently proposed generalized hydrodynamic equation to describe transport near and far from equilibrium in quantum integrable systems. So this is a framework that was proposed 2 years ago in 2 papers, one by Bertini, Fagotti, Denardis, and others, and the other group of authors, Castro, Alvaredo, Doyon, and others. And so the question is if this kind of equation can be also explained from a purely in a purely classical system, or is it basically something that only makes sense in quantum mechanical systems? And in particular, what remains still a bit open question about this equation in the quantum context is how to derive it directly from the averaging of microscopic conservation laws. So this is something that remains to be done, and today I will show you how this is possible. It's possible to achieve this in the classical theories of solitons. And finally, I think it's an interesting question to address the notion of classical quantum correspondence, by which I mean to compare the out of equilibrium phenomena and transport on a qualitative basis between the quantum and classical systems. So should one expect agreement, disagreement, and I don't think this has been addressed in the literature so far. And to connect on this third point, I would like to highlight a paper by Tomasz Persen and Bojan Žunković from 5 years ago, which is basically what they did. They took the classical Landau-Lifshitz ferromagnet, they put it on a lattice, and then do Monte Carlo simulation to compute its transport properties at finite temperature. And remarkably, what they find that there is you can find 3 regimes. So again, you can find a ballistic regime with finite Drude weight. You can find the normal diffusive behavior, or you can even find the anomalous superdiffusion, depending on the value of interaction and isotropy. So in fact, what happens is that this, if you want, these phases, they are precisely in agreement with what Jacopo told you on Tuesday, in agreement with the transport properties of the Heisenberg quantum spin chain. And so it would be nice to understand why this is so. Okay. Right, so yeah, so basically what I mean by theories of solitons, I mean integral partial differential equations. So here I just listed a few most prominent examples. So historically, the most important role played the Korteweg-de Vries equation, which describes shallow water waves. It's a scalar field theory. Then is the nonlinear Schrödinger equation, which is the basically classical version of the Lieb-Linear model that Joachim was talking about previously. Sine-Gordon model, and there is countless many other models. What those models have in common is that they exhibit nonlinear stable excitations, which are known as solitary waves or simply solitons. But typically, also besides solitons, there is other type of modes, other components in the solution, which pertains to the continuous part of the spectrum, which is often referred as radiation. So here is a cartoon of what will be a typical situation if you start with some field configuration for a scalar field theory, like a KdV. You will get a bunch of solitons, and you will get some radiation or continuous part. So this model in particular is a bit special because the solitons move in one direction, and continuum is only allowed to move in the other direction, but generally you can have like bidirectional motion, of course. And the solitons are again like some nonlinear field configuration, which have this distinctive 1 over cos square profile. All right. Next. Okay, we have some problem. All right. Today I will be talking, I will focus exclusively on the Heisenberg field theory. And the reason for that is because we understand the Heisenberg spin chain theory quite well. And this particular classical system basically is a classical limit of a spin chain. I will tell you a bit more about this at the end. And so this is the reason why I want to understand thermodynamics and hydrodynamics, why I want to address it in the context of the Heisenberg field theory. So it's equation of motion describes some precessional motion of a spin field. Yeah? So now we don't have a scalar field. We have a field where at each point in space and time there is a spin vector, which is normalized to 1. And, well, in the Hamiltonian, which governs this equation of motion, is given by this expression. One can also represent the dynamics in terms of the canonically conjugated variables. Then the coordinate will be the phi, which is the angle, the precessional angle, and the conjugate momentum will be the cosine of the polar angle, which is the z component of the spin. So this is one of the paradigmatic example of exactly solvable partial differential equations. And to solve this model, actually this explicit representation turns out not to be very useful. So how these equations are solved normally is that they get transformed, they get mapped into a different space. And this is what I would like to briefly outline. So essentially, the idea is to encode the spin field, in my case, into an object called a connection. So the connection I denote by U will be some matrix, which depends on space-time coordinates, and in addition on some complex parameter, which is called the spectral parameter. And it has two components, the spatial component and the temporal component. And the whole idea of having this connection available is then one can then use powerful methods of algebraic geometry to deal with this dynamical system. And I will explain you in next slides how this works. But the main property of this connection, which is basically the property which is synonymous to integrability, is that this connection is flat, or it satisfies the zero curvature property. So it means that if you take the two covariant derivatives and you compute their commutator, you will get 0. And if this condition is satisfied for these connection components, then it's guaranteed that your system will be integrable. So let's see if now, if this system is integrable, so it's not manifest, so one has to be smart and figure out what these connection coefficients are. And, sorry. And well, and it turns out that there exists such a choice for the Heisenberg theory. So if you take the special component to be this matrix of your spin field and the temporal component, this expression, it's not very important how they look like, just important that they exist. You plug them back into zero curvature condition, you will find that the curvature vanishes if and only if the equation of motion is satisfied. So the equation of motion is basically a compatibility condition for what people call an auxiliary linear problem. And so how it works now, instead of solving the original equation of motion, we now associate to it an auxiliary linear problem which represents a parallel transport of some matrix valued wave function, psi, which is governed by this connection. Yeah? So we have simply a system of differential equations where this wave function now evolves in space and time. Now, in order to completely fix the problem, one has to moreover impose the boundary condition. One has to choose the boundary condition. And here, typically, there is two possibilities. So most common in the literature is to assume open or infinite boundary conditions, which is to say that if you have a spin field, like in my case, that far to the right and to the left, the spin field just aligns along a fixed direction, say z direction. Yeah? So this is like the case into a vacuum, if you want. And then if you have this situation, you can exploit this useful representation and then kind of integrate the equation of motion within the formalism which is known as the classical inverse scattering method. This will not be the method I will use today, and the reason is this. If you use that method, basically what you're describing is a vacuum and excitation on top of the vacuum. And this is not what I'm after, because I would like to define the notion of equilibrium ensembles. And equilibrium ensembles are some statistical ensembles of let's say, we describe a soliton gas at some finite density of solitons. So in order to achieve this, in order to identify such a limit, it turns out that one has to impose periodic boundary conditions. So put the theory on a circle. And then with that, basically the appropriate method to solve the system is the so-called finite gap integration method. So now the plan is as follows. So first, what we need to do, we need to understand what is the complete space of solution of this equation of motion. Then, from this space of solutions, moreover, we are interested in identifying the most natural set of coordinates, namely the action angle type of coordinates, because this is where the motion of the system is most simply described. In terms of these coordinates, we will learn how to compute the averages of local conservation laws. And once we understand this, we will identify an appropriate thermodynamic limit. So we'll consider a state which has a lot of nonlinear modes in there. And then in this limit, we will be able to define the notion of equilibrium soliton ensembles. And once all of this is accomplished, then the last step will be to find the equation of motion for the adiabatic evolution of such equilibrium states. And this will be the hydrodynamic equation that I would like to obtain today. So how it works, basically the connection, which I just gave you on the previous slide, you take the connection and you integrate it. So now my space-time manifold is a cylinder, right? So time flows upward and periodic boundary conditions, so it means it's a cylinder. So the most important object in the game is the so-called monodromy matrix, where you take the connection and you integrate it around the world. So you get this matrix T. And now to classify completely classify the spectrum of the problem, it basically boils down to diagonalize this object. So we will have some eigenvectors, which depend on space and time, and we will have the eigenvalues. Now what is important is that because of the zero curvature property, it doesn't matter actually which path I take to go around the cylinder, along which path I integrate my connection. So by zero curvature property, I will always obtain the same result. And this will imply that the eigenvalues, which I showed you before, are not time-dependent objects. So they're really conserved in time. Moreover, since the product of eigenvalues is equals 1, I can parameterize them in terms of a single function p of lambda. This function p of lambda is called quasi-momentum and is the crucial object in the game. So from what follows, this quasi-momentum is the central object. So it has various meaning. Maybe one pretty natural meaning of this object is that it's analytic in this spectral parameter lambda, and if I expand it, I will find the average values of local conservation loss for a particular solution. Okay, so the task is now to understand what information does this eigenvalues lambda encode, and to also understand how to obtain the eigenvectors and what the information is stored in the eigenvectors. So let's first address the spectrum. So the spectrum of the problem is basically encoded in an object which is called the spectral curve. It's some curve in the complex plane which is defined by this characteristic equation. So it's determinant of the spectral determinant for the monodromy matrix. So you start with some field configuration, you compute the monodromy matrix for it, and you associate to it the spectral curve. And it's given in terms of the quasi-momentum by this equation. Now, as I said, this spectral curve is time invariant, and you can see it as being a double cover of the complex spectral plane, which is branched at some finite number of points, which I denote by lambda j. So what are these branch points? These are basically points where the spectrum of the monodromy becomes degenerate. So typically you have, for a given lambda, complex number, you have two distinct eigenvalues, but at some points it happens that the two eigenvalues coincide. So now one would like to understand this object, which is a little bit annoying because, in particular, it's not this equation does not describe an algebraic curve, and therefore you cannot directly use the methods of algebraic geometry. But fortunately, it's very easy to handle this. So what one should define instead is to define the logarithmic derivatives of the eigenvalues, which is the derivative of the quasi-momentum, or equivalently assign to the quasi-momentum the differential dp. And then you see this differential as being some differential which lives on an algebraic curve. An algebraic curve, which I denote by sigma, is again a curve in the complex plane, which is defined by this algebraic equation. So mu square of lambda is some finite degree polynomial of lambda. In particular, this is a hyperelliptic curve. So what is nice now that if I have a hyperelliptic curve, I can see it always as a hyperelliptic Riemann surface of some finite genus G. And then basically the game you play, you have this surface equipped with this differential, and from this you can with this construction you can classify the complete space of solutions. Now what is nice is that if you have a Riemann surface of genus G, what this tells you is that you are describing a solution of finite complexity, in the sense that it will have only G modes present in the system. Yeah? So it's a bit like a Fourier transform, where you can study a solution which has finitely many Fourier coefficients. So now the spectral curve is the object which gives you the complete information about the non-dynamical part of the solution, which means that we should be able to retrieve, to construct the action variables from it, and also the conservation laws. And in order to do that, what you have to do, you have to equip this finite genus Riemann surface with a homology basis. So you define a complete basis of cycles for this surface. So the cycle is just a loop. Just a closed integration path. And there is two types of cycles that you have. So there are cycles which, so here, for instance, I plot you kind of a very simple situation where you have two branch points, and then you connect them by a branch cut. And there are cycles which are such that encircle a branch cut, and there are cycles which are such that pass through a branch cut. So it means that if I have genus genus D surface, there will be a basis of G plus 1 alpha and beta cycle, alpha going around and beta going through the cut. If I go through the cut, basically it means that I'm starting on one sheet of the surface and then I'm jumping on the other sheet and I go back. For instance, you can define this cycle such that you go from infinity through the cut and escape back to the infinity. And now, with this construction, for instance, you can define the quasi-momentum differential in a unique way. So you prescribe the algebraic curve, and then by requiring that this differential is analytic, which amounts to normalize it with respect to alpha cycles, requiring that alpha cycles vanish, then this dp is uniquely fixed. And once you have it, you can take its abelian integral, and then you do this moment expansion, and if you sum over all the cycle, you will find the conservation law. So, in other words, if you have a particular solution to the equation of motion, there will be a particular function, quasi-momentum function associated to it, and then if I look at the expansion coefficients of it, I will find the average values of conservation laws for this particular solution. I mentioned already before that one can see this as basically as a nonlinear version of the Fourier transform, where if you have some periodic or quasi-periodic solution which contains n interacting phases, you will have n many wave numbers k and n many so-called filling fractions s. So wave number is, as you imagine, is a wave number like in linear equations, except that these wave numbers are now associated to some nonlinear waves. Basically elliptic or hyperelliptic waves. Is not really important how they look in the configuration space. What is important that there exists a notion of a wave number. And then to each wave which is present in the solution, you will basically associate also its intensity. So this filling fraction is basically the intensity of a given wave. And one is obtained by taking the beta cycle of the differential and one alpha cycle. So it's a very nice construction. And then if you want to impose periodic boundary conditions, which is what we want to do, then it just happens that these wave numbers will not be arbitrary real numbers. They will have to be quantized. They will become integers. And another important object is that there is this another distinguished differential in the game, which is called quasi-energy, which is also uniquely fixed, which you can construct, and then by evaluating beta cycle, you will get the frequencies which pertain to the wave numbers. So now it's basically really a nonlinear Fourier transform. We have finitely many modes, characterized by a bunch of frequencies and a bunch of wave numbers. So this is what the spectral curves give you. And then to have the dynamical part of the solution, we also have to find the eigenvectors. So the eigenvectors are the eigenvectors of the monodromy matrix. Now it turns out that, of course, the eigenvectors are not uniquely defined because normalization is arbitrary. But once you choose what is your reference vacuum, so you choose, for instance, vacuum to be the spin aligned in the z direction, then you can define the normalized eigenvector h, which is unique. And then it turns out that this normalized eigenvector is defined in terms of a single function. So h2 denoted here. And it's this function that contains the entire time evolution of a solution. So in particular, this Becker-Achieser function is a meromorphic function, and for a solution which contains n phases, it will contain n number of poles, gamma I. And these poles are the dynamical variables of your solution. And not only dynamical variables, very particular dynamical variables, because they are basically separated variables of your motion. What it means is that if you look at these poles, so they will move somewhere around this finite genus Riemann surface, but their motion is not just arbitrary. They cannot just wander around anywhere. They will be locked to a particular cycle. So for each cycle that you have, there is one dynamical pole which wanders around it. So you can find, of course, the equation of motion for this poles. It's still quite complicated, non-linear motion. And what is remarkable is that there exists a transformation which is called the Abel-Jacobi transformation from these variables gamma to another set of variables denoted by phi. You just evaluate some Abel integrals of holomorphic differentials. You find a new set of variables, and now these variables are basically the angle variables of a particular solution. So in particular, this mapping, you map your evolution from the surface to what is called the Jacobian. Jacobian is topologically a hypertorus, and then these variables are basically represent the winding around this hypertorus. If I express the equation of motion for these angle variables, it's very simple. It's just kx plus omega t, where these parameters I just obtained previously from the spectral curve. So what we did now is basically we found the integrability of this model and constructed the angle action variable in the sense of Liouville Arnold. The conjugate momenta for this phi are nothing but the filling fraction, which I also mentioned previously. Very good. So this is finite gap integration, but initially I promised you solitons. So where are the solitons in this picture, you may ask? Well, so since this M-phase solution basically describes interaction of some nonlinear modes in the system, which all have some finite periods. Strictly speaking, there is no solitons, because solitons are, as objects are objects with infinite periods, right? They are not periodic solutions. However, it turns out that also solitons can be retrieved if you take a particular degenerate limit of this surface. So what you have to do, you have to take a beta cycle of a surface, and you have to squeeze it to a point. So in the process, when you pinch one cycle of the surface, what you do is you reduce the genus by one unit, and when you do that, you generate a soliton on top of your solution. And then if you want to construct an exact multi-soliton state, what it amounts to do a complete degeneration of this surface. So pinch all the cycles, and you reduce genus down to 0. And so it turns out that with this procedure, you will recover the Heisenberg precessional soliton, which, well, it's described as has some dispersion relation of this type, which you will recognize is basically exactly the Magnon. It's like the Magnon dispersion relation. So the bottom line here is we do have solitons in the game. They are just a particular limit of the curve. Now, a few more words about solitons. So solitons are funny objects. So if you look at them asymptotically, so where they're very far apart from each other, they're like free particles, and the solution, a two-soliton solution, would then be a simple superposition of individual solitons. But when they are close to one another, their interactions are strong, nonlinear, and they get appreciably deformed. However, what is remarkable is, so here is a cartoon of a solution which has two solitons only when a fast soliton is taking over the slow one. So in the intermediate time, some stuff happens, but after a long time, both solitons re-emerge, non-deformed. The only thing that happens is they get the center of mass. So think of this is maybe some scalar field. So then you can see that the center of this peak will acquire a small displacement, and the other soliton as well. So the whole effect of an inter-soliton interaction is just some center of mass shift, if you want. And if you have more solitons in the game, then the total shift is just a sum of two-body shifts, so which shows you that there is the notion of a complete two-body factorizability or reducibility of the dynamics, which is another hallmark feature of exactly solvable or integrable systems. So, well, the question is how to get to this, how to obtain this scattering displacement. And in particular, how to identify the notion of the classical S matrix to it, because it turns out that this will be the object that we will require to. It will be required to define the notion of equilibrium ensemble. So this is why it's important to understand where the notion of a classical S matrix comes from, and it comes from the intersoliton interactions. So. Because the solitons scatter completely elastically, the S matrix is essentially not a matrix, it's just an amplitude which is completely specified by a phase. And now this phase, basically, it's nothing else but the generator of a canonical transformation which connects two asymptotic states. So the solitons in the infinite past to the soliton states in the infinite future. And to compute it, you can use basically two complementary pictures. The dynamical one is to simply take the limit of the spectral curve where you obtain the solitons, solve the dynamical problem of solitons, and extract the phase shift from there. But there also exists a static picture, which is based on the computation of the off-diagonal elements of the so-called Riemann period matrix. So Riemann period matrix is you compute the beta cycle of your holomorphic differentials, and it turns out that the information that this object contains is the interaction between the nonlinear phases in your n-phase solution. So if I take now the soliton degeneration limit of this object, I will exactly retrieve the scattering phase. And finally, there's also like a short and more physically maybe clear route how to do that without too many technicalities, which is based on the Jackie-Wu semi-classical formula, which in a sense is a Born-Sommerfeld quantization for classical soliton orbits. So if you put your solitons in a finite volume, then you will have this Born-Sommerfeld quantization condition. And from there, you can basically derive a general relationship between the classical phase, as I define it here, and the center of mass displacement, which I denote by delta x of the solitons. And it turns out that you just take once you have the center of mass displacement, then you just do a momentum integral over it, and you will find exactly this phase. So, all right. So now I want to finally tell you how to obtain the thermodynamic soliton gas. So what is important to stress that naively one could think, oh, let's just take the complete degeneration of the Riemann surface where I get just like a gas of solitons, and then I do something with the solitons. However, technically speaking, this is not the right approach, because when you take the zero genus limit, what you will have some dilute state, dilute gas of solitons imposed on a vacuum. And such a state necessarily has zero density. Yeah? So there is a finite amount of charge in the infinite volume, so the density is zero. This is not what I want to do. So there must be another limit. And it turns out that such a limit exists, but it's a more subtle limit, it's some scaling limit. And it works like this. So you have to start with the spectral curve that I told you about. Now you take the circumference of the system L, and you make it grow large, but at the same time, you need to put the number of modes, which the spectral curve describes, also to grow large, proportional to the system size, in such a way that the sum of all the filling fractions is a fixed constant. So this will be the density of your state. And such a limit exists, and you can see it as basically an interacting gas of almost degenerate branch points of the surface. Yeah? And then the soliton excitations are basically the excitation which arises in the limit where all these nearly degenerate branch cuts collapse to a point. Yeah? So ultimately, when you take the scaling limit, indeed, you have this interpretation as basically as a dense gas of solitons, unlike this genus zero limit, which will give you the dilute gas of solitons. And moreover, such a limit, it also has a natural statistical interpretation, because when you take this limit does not see any time dependence anymore. So you can see it basically as a microcanonical averaging over all possible angles in a uniform fashion. So it can really be seen as a statistical limit. So there are further remarkable things. So now if you're taking this limit on the level of spectral curve, it looks a bit messy, but then what you realize that if you retain just the leading term in the system size, then the expression you are dealing with can be cast basically in this type of condition, which many of you will realize as a beta equation condition, so the equation that gives you the quantization of wave numbers for interacting particles which are subjected to periodic boundary conditions. So now the entire effect of all this gas of branch points, which when collapsed give you soliton excitations, all of that just becomes like a product of scattering, classical scattering phases, which we know how to compute. And on all the rest, for finite L, there are correction terms which don't matter anymore. So ultimately what we have now is like a classical beta equation for a soliton mode, and each soliton mode is described by a single complex variable, which is its action variable. Yeah? So now I have basically a gas of soliton action variables, and I can basically employ the standard machinery of well, the standard beta ansatz logic if you want. So I go quickly through this. So basically what you do, instead of dealing with the discrete set of action variables, you just introduce the soliton spectral density, so a continuous density of this of the action variables. Then you define the notion of the total state density, which is the density of all available modes. Now, this is a non-trivial object because of the interactions between solitons. And you can define also the occupation functions, which is the ratio of the two. So this is really, those who are familiar with the thermodynamic beta ansatz, this is the philosophy of Yang and Yang, which is known for 50 years or so. So what you get then, you have a linear integration equation which relates to the, which is an equation for the total state density expressed in the terms of the mode occupation function. And now this mode occupation function is where the state dependence enters. In particular, when we define an equilibrium state, the equilibrium state basically amounts to give a particular mode distribution function. You plug it here, we have the total density, and then everything else is determined. So I need to go a bit faster. So, and how to fix this with this mode occupation functions? Again, the way it works is that you are basically summing the partition function for the model, but if you express it in terms of the action variables, it's a diagonal object, so it completely factorizes. When you go to the thermodynamic limit, you can turn this summation into the functional integration for the soliton spectral density, which allows you to cast the equilibrium free energy density as a functional of the spectral density. So there are some parameters which are free, and these are basically the chemical potential of your equilibrium state. So the chemical potential for the total charge and for the local conserved charges. So with this, if you want, we are describing a generalized Gibbs ensemble for a classical soliton gas. And S is the entropy factor, which gives you the logarithm of the number of states in a small rapidity interval. And it's basically the Maxwell-Boltzmann entropy of this dense soliton gas. You take the, in the thermodynamic limit, what you have to find is the saddle point configuration, and this gives you the thermodynamic beta ansatz type integral equation for the logarithm of the occupation function. It's expressed like this. You can see this equation, an alternative interpretation of this equation is basically the dressing of energy. So if you have an individual soliton with energy E, now this soliton being superimposed on some non-trivial many-body background of other solitons, because of the scatterings, it will dress, and instead of having its bare energy E, it's kind of a thermodynamic energy it's different, and it turns out to be nothing else but the thermodynamic limit of the quasi-energy, which I told you before. So in other words, if we had the quasi-energy gives you the effective or the dressed energy of interacting nonlinear modes in a finite gap solution. Now, once you take the thermodynamic limit, this object will give you the dressed energy of a soliton excitation in a dense soliton gas. Okay, so we understand how to do equilibrium, and the last part is to derive the hydrodynamic equation of motion. So now we want to go out of equilibrium, but only we would like to understand how the evolution, how the equilibrium responds to very large and slow spatiotemporal modulation. So basically, what we aim to do is to derive the Widen modulation, to leave the modulation theory for finite gap solution, which is known as the Widen modulation theory. We want to lift it to the thermodynamic setting. So how it works, let me first briefly say how it works for solution with finitely many modes. What you want to do is basically you want to adiabatically want to slowly modulate a particular solution. So this will require some separation of length of time scales, and there are two ways to see how this happens. So one way is to think of take a particular solution. Its motion is described by evolving action variables. Now these variables, you can see them as fast variables, But then on top of this motion, you can think of the you can think of the parameters of this solution as being slowly dependent on space and time, but such that their dependence is much slower than the frequency and the wave vectors which govern the fast motion. Yeah? So in other words, parameters of a solution slowly changing over space and time, you can see them as slow drift of conservation loss. So this kind of statement you can express in terms of a continuity equation for the meromorphic differential of the finite gap solutions, and which is of this form. So this is now the slow drift of local conservation loss. The other interpretation of this, which is geometric interpretation, is that you see like you have the fast motion, which is governed by these variables, and which live on a Riemann surface. But then this Riemann surface is not stationary like originally, but you promote it to a time-dependent object, such that it breathes on a much slower scale than the intrinsic motion of your solution. Yeah. So basically, what you do, you take the branch points of this Riemann surface and you start to slowly move them. What you find is the equation of motion for the branch points, which is characterized by a characteristic velocity v effective. And these velocities, how you determine them, it's again, you take these distinguished differentials, the quasi-energy over the quasi-momentum, and you evaluate it at the branch point. And it will give you the kind of characteristic velocities for a modulated solution. So this is the finite gap setting. Again, we are interested in the thermodynamic limit. We want to leave this to the thermodynamic setting. And basically what you need to do, instead of modulating individual branch points, now we are modulating the soliton spectral density itself. So we promote it from a stationary object to a time-dependent object. And what this gives you is some adiabatic spectral flow, which is governed by this continuity equation for the soliton spectral density. And now the spectral flux is nothing but the soliton spectral density itself multiplied with the effective velocity. And the question is, what is this effective velocity? You find the equation for it, and you see that it's again nothing but the thermodynamic quasi-energy over the thermodynamic quasi-momentum as a function of the soliton action variable tau. And it satisfies this integral equation. So you can see it basically, you take the group velocity of an individual soliton, and then it gets dressed by the presence of a multi-soliton background with this term, which depends on the scattering phase shift, the density of solitons, and the relative difference of the effective velocity. What is remarkable that once you find this, you basically recover the so-called generalized hydrodynamic equations that Jacopo told you about on Tuesday, proposed by Castro Valledo et al. And Bertini et al. So if in this formalism, you get exactly the same equation. So basically what I show you is that you can find it from a particular scaling limit of the spectral curve. And this result is also, must mention, work by L and Kamchatnov, where they obtain the same equation, but for the case of the scalar KdV theory, where they find this equation comes out from a certain continuum limit of the Riemann theta function, which was previously worked out by Venakides. So here I gave a bit more physical, intuitive approach how this equation comes about, and I also was able to link it to the thermodynamics. So in this work, basically, they arrive at this equation. The trick is that for them, this density was somehow introduced at the phenomenological level. So what we were able to achieve now is that we understand that this density is basically the soliton spectral density, which can be linked to thermodynamic soliton ensembles, essentially in the fashion of Yang-Yang thermodynamics. So now we can really do finite temperature or physics for solitons. All right. Maybe just briefly what happens if you go from classical solitons to quantum solitons. So once you have this Lux connection, so zero curvature formulation of the problem, it turns out that it's not really difficult to find the associated quantum mechanical integrable system, because you simply take this connection, you quantize it, and you are in business. But there will be certain differences. So a most prominent one is that quantum solitons, by quantum solitons, I mean the solutions to the quantum mechanical equation of motion, if you want, or Bethe-Ansatz wave functions. They carry a discrete amount of charge. So instead of having a continuous variable tau, my soliton action variable, which basically is two-dimensional, it has two real degrees of freedom. What you will have one discrete degree of freedom, which is the quantized spin, and then one continuous degree of freedom, which is the momentum of a quantum soliton. So this is a new feature of quantization. It's pretty obvious. The other feature is that if you look at quantum excitations and what statistics they obey, you will learn that you can't excite one excitation multiple times, so there is no higher excitations, which means that excitations are basically Fermi-Dirac particles, so you have to use adjust the entropy factor accordingly. And finally, again, obviously, instead of the classical S matrix, what you will have in the formalism will be the exact quantum S matrix. All right, so in 3 minutes, maybe I can say a bit about. So I was talking about I was telling you about the classical Heisenberg ferromagnet, and until this point, I made absolutely no reference to quantum spin chains. But if you remember, originally I wanted to motivate the study of this problem in the context of comparing its physics with the Heisenberg spin chain. So now I just want to mention how the two are related. And in fact, it turns out that this classical Heisenberg field theory is nothing but the low energy regime of the ferromagnetic quantum spin chain. And there is 3 ways how you can derive this or justify this. One is to simply find the Lagrangian for the effective theory, which describes the long wavelength modes of the Heisenberg spin 1/2 chain by projecting out the long wavelength spin coherent states. The other possibility is to consider integrable spin S models with large spin, take the large spin limit, and take the continuous limit. Then you will also recover the same theory. And the third possibility is to simply stick with the Bethe-Ansatz for the Heisenberg spin 1/2 chain, and then consider the semi-classical part of the spectrum. Maybe just in a picture. So what happens, for those of you who are familiar with the Bethe-Ansatz for quantum models, so the semi-classical part of the spectrum are solutions which are described by quasi-particle rapidities, which are large. This means that the magnons, which are involved in these states, have low momenta. So it turns out that there exist states which have macroscopically many bound magnons in them. So there are really large coherent bound states of magnons which appear in the spectrum if their rapidity is very large. And then what happens that this kind of solution, once you take the semi-classical limit, will basically become a nonlinear mode which is present in this, so the nonlinear mode which is present in a finite gap solution, which I was describing earlier. In other words, so the nonlinear modes, which in some particular limit become the classical soliton excitations, they are macroscopically bound state, macroscopically large bound state of Bethe roots. And then if you derive, if you see what the Bethe equations gives you in this particular limit, so you can define the resolvent for these Bethe roots, which condense along some contours. You will see that the equation that you have, it's basically equivalent to the equation the equation for the quasi-momentum, which tells you that the quasi-momentum is nothing but the resolvent of the Bethe root. So that's kind of a very interesting relation, which is, if you do classical integrability, a priori you might not realize that these branch cuts, they have a physical interpretation, that they are basically made of Bethe roots. So basically, another way to see what I was doing today is to start with a quantum mechanical model and consider the spectrum in this limit, and then it's natural that the equation that we recovered exactly match those equations that were previously found by other authors previously in the context of the quantum spin chain. And that's it. I maybe want just to summarize the main result, just to read the main conclusion. So we were able to derive the hydrodynamic equation of motion for a dense soliton gas. we found that the statistical ensemble corresponds to a particular scaling limit of a nearly degenerate Riemann surface of large genus. Each equilibrium eigenstate can be seen as a microcanonical ensemble of solitons and is assigned a unique soliton spectral density. Then the hydrodynamic equation, which we derived, is basically the thermodynamic analog of the Wida modulation equations, which were known for the class of finite gap solutions. And one interpretation of this hydrodynamic equation is that it governs a slow drift of the average local conservation loss of the model. And this equation is completely encoded by two distinguished objects, which are called the quasi-momentum and quasi-energy. And so if you think about the quantum soliton theories, then you can say that this hydrodynamic equation called the generalized hydrodynamics is basically the adiabatic evolution of the quantized spectral curve. Yeah, so, and with this, I will thank you for your attention, and yeah.
Construction allow for identification of the currents appearing in continuity equations for the higher conserved charges of the spin 1/2 Heisenberg chain. I mean, we have infinitely many conserved charges. We know they are local, and we speculate that also currents should exist which are local and satisfy the continuity equation. So can you construct that maybe in a semi-classical limit and maybe just close to the ferromagnetic point, although we are interested in the antiferromagnetic system?
So you are asking me if I understand about the analogs of higher conserved charges for the semi-classical spectrum.
And the continuity equation and the currents. Yeah, I mean, we know the thermal current for the local Hamiltonian. Yeah, so that is known, but for the higher conserved charges, we don't know these local currents.
Exactly. In the quantum spin chain, right?
The continuity equation.
In the quantum spin chain, we don't know how to realize the current as an operator which acts on the,
right.
on the
This
spin
is
chain.
a question. Yeah.
But in the semi-classical limit, then basically what remains, the whole semi-classical spectrum is governed by this finite gap. It's parameterized by finite gap solutions, which are completely parameterized by the single function, the quasi-momentum. So the local conservation laws are just the expansion coefficients of this quasi-momentum. So there is no room for additional charges, because that would mean that you have an additional conserved object in the game, which you need to take into account in order to get some new solutions. The statement is there is no new solution. It's only the quasi-momentum, which is basically completely describing you all conserved quantities, the model, and is the quasi-energy, which gives you the associated fluxes. So these are the only two objects. So, and once I understand those objects in the context of finite gap solutions or in the thermodynamic limit, as I said, I should be able to exhaust the whole space of solution. This is my current understanding. In the quantum case, it's different because you have like the bound states of magnons, so the kind of magnons come from fusion of elementary magnons, so therefore it's natural that you have higher dimensional, so charges which transform according to higher dimensional representations. But in this limit, I don't think there's such a thing.
So conceptually speaking, this kind of hydrodynamics wouldn't be the same as the sort of generic one that we heard about yesterday, because there's too many conserved quantities.
Yes, exactly. But maybe one interesting. Yeah. Yeah, in a sense, it's maximally constrained because integrability imposes this structure on you. And, but you see that the complete space of solution is, again, encoded in a certain analytic object. And so what you need to do is just take the hydrodynamics of this object. If you want to retrieve basically equation of motion for individual quantities, say energy or some higher conserved quantity, you just have to expand the quasi-momentum. Let me say it in more simple terms. What you could do in principle you can stick, let's not go to the thermodynamic limit, let's just construct the most simple finite gap solution. It's such that it has just one mode present. So we have just one nonlinear mode in there, and now I can already do hydrodynamics. So now you can ask me how many conserved charges are in this solution. Well, infinitely many conserved charges, but all of them are functionally dependent because there is just one wave vector. So if I know the energy density, I know everything else. So basically, I'm just modulating the wave vector. I'm simultaneously modulating an infinite family of conservation laws. And then I can go to two-gap solutions. So I have two modes. Then I modulate two modes. And again, this will imply modulation of infinitely many conservation laws. There's always infinitely many conservation laws, but they may not be functionally independent.
And even more specifically, you showed this integral equation for the velocities here on the previous slide. There were two velocities. Just, go back to one of those previous. Give it this way. So what's known and what is to be determined in this equation?
Right. So the input, so first, the group velocity of a soliton is known. It's, again, it's obtained from its dispersion relation, Baire dispersion relation. The interaction, this is the displacement when two solitons collide, is related to the scattering phase, which I showed. So again, you know what it is. It's an intrinsic property of your system. And the effective velocity is what you're computing. And so the only state-dependent object is the blue one, is the density. So if you give me a Gibbs equilibrium state, means you say there is some temperature, I will use the equations on the previous slide, and I will compute a unique density. I will plug it into this equation, and then everything is determined. If you give me some other state, some other equilibrium state, not Gibbs, again, you assign some chemical potentials. This forces a particular distribution of soliton action variables. It comes with a particular density. Play the same game.